I'm going to talk about making a peer-to-peer Dropbox and kind of like the implications of that. And yeah, let's get started. So I'm Mathias. I go by Macintosh on GitHub, Twitter, and Instagram now. That's where I put all my Russian food now, pictures of that. It's pretty cool. Surprisingly good food here, by the way. I'm very blown away by the amount of good food in Russia. I don't know why I would expect there not to be good food, but you know. Stereotypes are weird. It's very similar to Danish food also. Anyways, I live in Copenhagen, Denmark. And yeah, I work on this cool project called the DAD project, and I will get back to that. It's an open source data science project that's funded by this cool nonprofit called the Alfred P. Sloan Foundation, which basically pays us to do open source every day. So thank you, Alfred. It's kind of nice. We get paid through grants, and everything we do is nonprofit and open. So it's a really really nice. I have nothing bad to say about that. I compiled these fun stats. We're an 8-person team. We recently grew from 3 to 8. We're all distributed. We're based in 5 countries, basically. I'm the only one in Denmark. We have 2 in Germany, 1 in Holland, 2 in the US, and 1 in Taiwan. So we kind of cover all time zones, and we're all remote. We have published more than 1,500 node modules altogether on our team, which is a few. I always have this stat here because I publish the most. Like 500 of those are mine. So that's cool. It's actually around 0.5% of NPM. So if you ever install 200 modules, you're welcome. Yeah, so our mission statement is kind of this. It's like we make tools to help scientists share data, right? It's kind of fluffy on purpose because that means we can do kind of what we want. Also, not just scientists, we want to help everybody share data. And when you talk about data, data is like kind of like a word that doesn't really mean anything, right? It can mean, depending on who you ask, they have a different opinion about data. Well, I generally think that data is just files. Somehow, somewhere, there's some files, and they contain some data. And it can be anything. It can be like, you know, data of cool places in Moscow. I'm interested if anybody has that data. Although we've already seen a bunch of cool places, so. It can also be like stuff like neuroscience data. We do a lot of work with that, or like earthquake data, a bunch of CSV files, any kind of data, basically, pictures. Movies are actually also data. You know, when they do neuroscience, when they do like brain research, it basically just boils down to a big microscope filming a brain and making a video file. So videos are data. Everything is data. Data is files. Yeah, so. Basically boils down to sharing data, just boils down to sharing files. And I have a lot of opinions about that. So sharing files, right? There's a bunch of great tools out there already for sharing files. I bet everybody in here at some point in their life has used Dropbox. I have. I'm a big fan. Dropbox is extremely easy to use. It's the kind of program that transcends all ages on a computer because it's just a folder, right? You just install it, you have a folder, you put files in there. Files get replicated to your friends that also has Dropbox. There's like no UI unless you want to do advanced things. Very few applications have this feature. Dropbox is centralized though, which means that when you put data into it, it uploads to a server somewhere. That server is run by a company that's in America, money for it. So the more data you put in, the more money they charge you. That's kind of not so nice if you put a lot of data in. It also opens up a couple of interesting questions, like when you put data in there, who owns the data? Because it goes to some server you don't control. What if they go bankrupt? What happens to the data then? Stuff like that. It also opens an interesting question about sustainability, right? If I have a data set and I want to share it, but I want to share it for 20 years or 30 years, can I rely on Dropbox being around for 30 years? I don't know, it's been around for what, like 5, 10? 30 years is a long time in computer history, but we'll probably all be around in 30 years. So it would be nice to know that your data is around also. So yeah. Then there's also stuff like BitTorrent. I've done a lot of stuff with BitTorrent before, and I'm a huge fan. BitTorrent is decentralized and peer-to-peer, which means that it doesn't have the sustainability problem that Dropbox has, because as long as you have peers seeding your data, you're fine, right? It's not as easy to use, unfortunately. It's like you have to install an application, you have to know how it works. Most people haven't even tried creating a torrent, to just try downloading torrents for various purposes. So, yeah. It is massively adopted though, which is super cool, which means that it's probably the most adopted peer-to-peer network out there. A lot of people have a BitTorrent client, and compared to other approaches, no one really comes near it in terms of adoption. There's like millions of people running BitTorrent all the time. Also, if you're technical and you study it, it's actually a surprisingly simple protocol. It's something you can probably, if you're familiar with networked applications, you can sit down and implement in like a weekend, honestly. Like a very simple version of it. You should not underestimate that. Most peer-to-peer networks do not have this feature. They're like insanely complicated. It only works for static files. So by static files, I mean you can only take some files and put it into a torrent, but then you can't change the files anymore. If you change the files, it's basically a new torrent. So that's fine if you're sharing something that's static, but it's not very nice if you're sharing a data set that gets updated every day, because then every day you need to publish a new torrent. And then people need to go through the work of getting a new torrent every day. So it's like pros and cons. Also, it actually doesn't scale that well when you put in really big data sets. So I work with neuroscience a bunch, and data sets in there are usually in the terabytes, sometimes in the petabytes. BitTorrent doesn't really work that well for that because of some technical issues, because it was made 10 years ago where, like, gigabytes was pretty big data. That's fine. That's fair. And it's still only used for data sets that are around a gigabyte, like movies. So, yeah. And finally, it's kind of in the bottom, but it doesn't support diffing. So if I make 2 torrents that have the same file except for like one small bit, I have to re-download all the data every time. So even if I were had a data set that was updated every day and I published a new torrent, every day people would have to download all the data again. Which is, again, I mean, if you're sharing terabytes of data, that's not very cool. So I think we can do better. I think we can make newer systems that work better than this, or more ambitious, and have different use cases. So basically, we want to build something that's like easy to use, but not centralized, like Dropbox, right? So we're gonna have we want to take the nice thing from Dropbox. We want to have something that's basically decentralized, peer-to-peer, but basically not built for piracy, as BitTorrent is. I mean, we can all come up with use cases for BitTorrent that's not piracy, but let's face it, it's like 98% of everything out there. Which is too bad for BitTorrent because it's a cool protocol. I wish it was different, but it's not. Also something that's built for like modern use cases, such as ever updating data sets, huge data sets, terabytes of data, and especially from my point of view for scientific use cases. So something that works well for scientific data, which is basically big CSV files or big movies or brains. Yeah, so we basically need a next generation file sharing tool. And just to reiterate what that means from my point of view, it means something that's real time or live. I mean, we all deal with Node here probably. We like real time. That's why we probably got started with Node in the first place. You want to have something where you can share a terabyte of data, but only get the megabyte out that you're interested in, or everything. And you want to have something where you can kind of subscribe to updates and get updates every time the data changes. We want to have it be decentralized, like I said. We don't want to deal with servers. We don't want to pay for servers. We don't want to deal with data centers, because data centers is just a fancy way of saying a bunch of servers. Sometimes when people use this word serverless, they just mean data centers, but it's actually just a bunch of servers. You should just call it a bunch of servers instead of serverless. We want to have something that just works on our cool laptops. Yeah. And finally, we want to make something that's diffable. So something where if I share a data set, and this is especially important for science actually. So if I share a data set, and then my colleague who I haven't talked to share a similar data set, if I'd ever downloaded one of them, I should only download the diff to get the other one, even though they're not semantically related. That's super important because there's a lot of redundant data out there. So spoiler alert, we already built this. It's called that. It's like my first slide. But before going into demos, how it works, I'll tell you basically how it's made. Have anybody ever watched this program on Discovery Channel? It's like my favorite program of all time. There's also a bunch of them on YouTube now. It's basically just people going around factories filming how things are made. Super good if you're into like making things. Anyways, basically everything to fix all these problems, everything boils down to this really cool concept that I'm super into called Append-Only Locks. Has anybody in here ever heard about Append-Only Locks? Oh, there's some cool people here. Cool. So Append-Only Locks is cool because it's self-describing. It's basically just logs we only append to. So like it's a list of data and you only ever append to it. There's only one problem with it, in my opinion. When we say logs, people think of very different things. I personally thought it was like log files initially. So we should just rename it to lists, append-only lists, because that's basically what it is. So let me show you a quick example and change your lives. So imagine you have a piece of data. It could be like a chat message, or it could be like a small picture, or like any data frame. You just take that data and you append it to a list. So when we first append it to a list, the list is empty. So now it just contains one data item. And we're all computer scientists, so we call it 0 instead of 1, because that's how you're talking to cool people. Then next time you have a piece of data and you want to append it to the list, append-only list, you just add it and you have a new piece of data. So now you have an append-only list containing of 2 pieces of data. And then when you have another piece of data, you just append it again, right? Super simple. That's all an append-only log does. You're only ever allowed to do this. You're only ever allowed to do nothing or append data to it. So you're probably all thinking, why append-only logs? That's like silly. Well, let me tell you why you should all start doing cool stuff with append-only logs. First of all, it's a simple data structure. It's something you can implement with just an array. It's immutable. It's like the keyword of JavaScript these days. You cannot change it. It never changes, which is really good for peer-to-peer systems. It has something called logical ordering, which means that the first item is called 0, the next item is called 1. You know that 0 came before 1, because 0 is less than 1. It's super important. It's like, sounds really trivial, but it's super important and has huge implications for distributed systems. It's also something data structure that's really easy to digest and index. So basically, if you have an append-only log that has 10 items, and I want to tell somebody which items I have, I just tell them the numbers in the append-only log that I have. So if I have the first item, I tell them I have item number 0. If I have all the items, I just tell them I have items 0 to 10. It's kind of like a digest. It always becomes very small and fits in very few bytes, which also makes it really good for distributed systems because they're very easy to share, very efficient. So I'm almost done with my theory here, but I want to educate you a little bit more. So if you have an append-only log, how can we share it? And especially, how can we share it over a peer-to-peer network where we don't trust anybody? Well, we can use this really cool other data structure, and that's my second most favorite data structure, called the Merkle Tree. Has anybody heard about Merkle Tree? And see the append-only people raising their hands again? That's cool. So a Merkle and the Merkle tree is basically just a tree structure that verifies data, which is like, that means nothing. It's also unrelated to Angela Merkel, the Chancellor of Germany. Although if you Google for Angela Merkel trees, you get all kinds of pictures of Angela Merkel in front of trees, and then she's usually pretty happy. So, I mean, probably also likes it. Anyways, let me tell you how it works. So, like, let's assume we have a append-only lock that we append to, right? So, this append-only lock only has one piece of data. So, a Merkle tree is just a tree structure where you hash the data in your data structure to build a tree. So if you have one piece of data, it kind of looks like this. So you have one piece of data, you hash it. We call that hash a root hash. If you have two pieces of data, you hash the other piece of data. Now you have two hashes. Then to build a tree, you hash the two hashes together. We call that a root hash. It's different than the other root hash. If you have three pieces of data, we do the same thing, because we don't have a power of two children right now. We just hash the first peak and then the second peak here in the tree. It's kind of like, if you can imagine two trees next to each other right there. And if we add one more piece of data, it becomes a tree again, because now we have a power of two. So now we hash I'm missing a line there. That's unfortunate. Doesn't matter. So now we just hash the siblings and hash the parents, and then we get a hash out. So why is this super cool? Well, it's super cool because this hash up top, root hash number 3, because it's the fourth one we generated, that hash verifies all the data. So that hash up there verifies all the data down here, because you can take all the hashes and hash them together, and they have to add up to the hash, right? So if we trust that this hash is correct, we can trust that the data below is correct. So that's kind of abstract, but let me show you why that's super important. So if you have a peer-to-peer system, and you have Alice and Bob. So Alice is this cool girl on the left, and Bob is this cool guy on the right. And Alice wants to share data piece number 2 with Bob. So in our Merkle tree structure, somehow Bob has this hash up here. So maybe Alice sent him a cool text message saying, hey, here's a cool hash. You should trust this one. It's awesome. It's like the data set of cool places in Moscow. And Alice wants to send Bob data item number 2. The only thing she needs to do is send him these pieces of data. So she needs to send him the data piece number 2. She needs to send him hash number 6 and hash number 1, which is a little bit magic. So let me show you why. So assuming Bob gets this data, and assuming Bob trusts the root hash, what he can do is he can just hash data item number 2 down there. Then he gets the hash of that. Then he can just hash number 4 and 6 together, because he has those two now. Now he has 5 and 1. He can just hash those two together, and he gets the parent hash. And now the only thing he needs to do is check that the parent hash hashes to the root hash. If it, yeah, it hashes again. If it does, then you know that data hasn't been tampered with if he's using a cryptographically secure hashing function. So that's super important. It means that if you have a data set that has a bunch of data, you can get any piece of data and verify it if you just trust that one hash. It also means that Alice only needs to send big O notation of log n of the amount of data she has hashes to Bob. So if you're not familiar with the log notation, it's basically just a very fancy way of saying the height of the tree. So if you have 4 in the bottom, the tree will be 2 high, that's log 2. If it's 8, it will be 3 high. So it's like a function that makes a big number a lot smaller. So basically that just means that it's just a fancy way of me pretending to be smart and saying she doesn't need to send that much data to Bob to verify it. It's also an algorithm you can easily optimize to never send the same hashes twice if they want to get 2 pieces of data. And I can talk about this for like ages. Just buy me a beer and you'll be tired of me, I'm pretty sure. So finishing up with the theory. we want to have this be real time also. So it's an append-only log. So every time we append data to this Merkle tree, we have a problem because the root hash of the Merkle tree changes every time we append data, right? Which is not very good because we need to trust the root hash to trust the data. That means that Alice has to send a bunch of text messages to Bob all the time with a new root hash every time she updates the data, which is not very cool. But luckily, we can just apply a little bit of crypto to make this all a lot easier. So basically, what you can do is you can just generate a key pair, cryptographically safe key pair. Oh man, I managed to put those boxes in the wrong location there. Anyways, generate a key pair. Key pair is just a fancy way of saying something that's secret and something that's public. And then, assuming that Bob trusts this public key, what Alice can do is that when she generates her Merkle tree, she can just use her secret key to sign the root hash. So then when she appends more data to her data structure, she gets a new root hash, and she just signs that one again with the same key pair. And since if you have the public key corresponding to the secret key up here, you can verify these signatures, which basically means that if Bob just has this public key once, he can use it to keep verifying the root hashes, which means that we can keep growing the data structure. So that was all a bunch of theory. I hope you're pretty happy about that. I am. I like theory. So luckily, I took all this stuff and I put it into a node module. It's called Hypercore. And I'll try to give you a demo of that right now. Cool. So let me see if this works. Command F1, right? Yeah, cool. Thomas just learned me some new tricks. So, gonna write some JavaScript now. Oh shit. So let's call this Hypercore. So Hypercore is just a node module that you can require that has this data structure. And the cool thing about it is that it's pretty easy to use. So you just require it, step number 1, as is the first step with most node modules. Then you need to require something called level.db because it needs somewhere to store these append-only locks. And I just like to store them in level.db. Then the thing you need to do is instantiate it, as you also need to do with most node modules. I just create a level.db and I create a hypercore. Oh, I should probably call this something else, core. Cool. Then, once you have a hypercore, you can create a new append-only lock. And when I made this, I decided to call them feeds because they sounded like Twitter feeds, which I kind of, Twitter feed is actually kind of like an append-only log, assuming you don't delete your tweets. I never do because all my tweets are funny. So you can just create a feed. And this is basically it. The cool thing about this feed is that it's an append-only log, so it probably only has one method, and it's called append. It actually has more than one method, but anyways. So I can just append any data here, a string or a buffer. I'm going to append this cool message called Moscow. And then I'm also going to print out the key of the feed, which is this public key I talked about before. And this is a buffer, so I'm going to print out as hex, because hex is cool. So let's try and run this. So when I run this, nothing happens. It just prints out this public key. But the cool thing is I can actually take this public key now and go back to our program and create the append-only log with this public key to kind of get the same append-only log out next time. And then instead of appending more data to it, I can create a read stream and get the data out of it, because append-only logs also allow you to get the data out of the log again. It's pretty cool. So I'm just going to print it out. So let's try and run this. So I can get the data out again. Pretty cool database so far. Put data in, get data out. It's like pretty essential. We can even append more data. I can be like, hi Moscow, because it's a little bit more casual. And let's try and run that. And then I get 2 items out. So it's append only. We can only append to it. Right? So that's kind of boring. But the cool thing is that this is a distributed data structure. So this key here actually verifies the data as I talked about. So what I can do is I can use this cool module my coworker wrote called Hyperdrive, and I can just add some magic here where I just call this around the Append-Only Lock. And what this does is that it spins up a network swarm that allows other people on the internet anywhere in the world to discover this Append-Only Lock, assuming they have the same key. Actually had and it's doing stuff like UDP hole punching to traverse firewalls also. So even though you're just on a normal computer and somebody else is on a normal computer, it'll do a bunch of network stuff to actually make sure that they can connect to each other. And it'll use the same security model as I described to exchange the data. I actually had a fun joke about firewalls here, because I think in Russia, instead of calling it firewalls, you should just start calling it networks. No? Anyways. So let's try and run this. So I'm just going to stop appending to it and start printing it out. So if I run this now, I get the same key out, but notice the program didn't stop because it's still running. But what I can do now is I can SSH into another machine, and I have another machine. This machine is in Germany, I think. And I can go in and I can take our program and I can just copy paste it. That's like my favorite way of deploying programs these days, just copy pasting code. And then let's, oh man, VI, it's like that. Yeah. There we go. And I'm gonna do one trick here where I'm gonna say, hey, make this live. So that means that it just keeps on reading data, it never ends. So let's try and run this program. So hopefully, when I run this program now, it will find the other machine and replicate the data. So that's pretty cool. So we can very easily replicate the two data structures together over the internet. The data is in a level DB. So it's just a folder. Yeah. So it's on both. So the cool thing is we can just modify our local program a little bit here and do this cool thing. Hook up to standard in and then do feed.append data to string trim. So this is just listening on standard in, and every time there's a message on standard in, it just appends it to the log. So if I run this program now, if I type a message here, it'll automatically replicate it because it's a live data structure and it's using this Merkle tree to figure out that the data is actually correct. And you can run this on as many computers as you want, and they'll all connect to each other, or like a subset of them, and start swarming and exchange data, and they'll get a little bit of data from everybody. So I think that's pretty cool. So let's go back to this. Gotta check the time also. Cool. Yes. So that's Append-Only Locks. They're cool, they're simple. I mean, the API for this is like very, very straightforward. You can get data in, you can get data out. You can also choose only to replicate a subset of the log. You don't have to replicate everything. You can just say, I just want to get the latest item. So for example, if you're using this to build something like a chat application, distributed chat application, you probably only want to replicate the latest message because that's the most interesting one in a chat program, right? You don't want to hear what somebody said a year ago. But you can choose to do that also. It's very flexible. So how can we take Append-Only Locks and turn them into a file sharing tool that we can use for science and stuff? Well, it's pretty easy if you think about it, because if you have a file and it's just like a bunch of bytes, what you can do is you can just take this file and kind of chop it up into like arbitrary sizes, probably small, so they fit in a small buffer. And then the only thing we need to do is take all these pieces of data and put them into an Append-Only Log. And then we kind of have a file sharing system, because then we can put data in and we can get data out. It actually has this cool added property, because we can do a cool thing to make this diffable. So if we insert a file into this append-only log or any kind of data, and somebody else has another append-only log that's the same kind of file, we can do some magic to make sure they only exchange the diff. So let's talk about that for a second. A little bit more theory, and then back to cool demos. So diffing basically just means you have a file, and yeah, cool. You have to divide it up into chunks that are unlikely to change. So if you look at something like Git, Git only deals with text files, right? So if you have a text file, chunks that are unlikely to change in a text file are just lines. So you just divide a text file into lines. Then if you change one line, it's cool because the other lines didn't change, because you're usually only editing one line at a time, which means that if you're using this in a system that diffs, you only need to exchange this one line now and apply that to the old diff to get a new file out. It's only one problem: it only works for text files. Luckily, I read this paper about this cool thing called Rabin fingerprinting, which is just some magic math that creates chunks based on actual content in a file. So that means that it's like an algorithm that scans through a file, and once in a while it'll emit a chunk, and this chunk is defined based on the content itself. Kind of like how if it was running on a text file, it will probably do every new line. And it's shift resistant, which means that if you change something in the beginning, it'll just shift all the chunks. So basically that means that if you have, if this is like a bunch of, if this is a file and it's been chunked using Rabin chunking, then you insert some data in the middle of the file. Rabin chunking kind of makes sure that only the neighboring pieces will change. Which is super nice because that means that most of the chunks are the same. And I wrote a node module for that. It's called Rabin. Rabin was available, so you can install that if you want to chunk a file based on that. So to do diffing, we just need to do a file, run it through a Rabin chunker, get these nice chunks out, insert them into an append-only log. So if this is like a bunch of Rabin chunks, you just need to, the first one is the first item in the append-only log, the second one, et cetera, et cetera. And then we just apply some Merkle trees to it, and we automatically get some cool diffing, because if this is a Merkle tree of the data, and we change the second piece of data, and Rabin chunking makes sure that these other pieces of data haven't changed, this basically means that in our Merkle tree, only these hashes will change, only the parent, and then the parent of the parent, and the parent of the parent. Which means that all the other hashes will be the same. So what we can do is, you can just keep an index where every hash points to all the data it spans. So in this example here, you keep an index that says, oh, hash number 5, the value of that points to data 2 and data 3. And then if you ever get a hash, and yet you've seen it before, you just look up in your local index and copy the data. It's very simple, very straightforward. Which means that you don't need to re-download data, which is cool. It will actually use more space because you need to keep this index, but you can apply some fancy tricks that are a little bit tricky to make it actually not use any space except for a little bit. So that's cool. So if you apply these two techniques, you can actually get a really cool file sharing system that supports diffing, and it's pretty simple. And I already implemented that. It's called Hyperdrive. I was very excited when I got that name because it's cool space stuff. But then somebody pointed out that it's actually it's the thing in Star Wars that never works. Oops, I don't know why my thing is not starting here. Oh, cool. Yeah, it's like every time in Star Wars when they're in like a situation where they kind of get out, somebody always says use the hyperdrive, and then they hit it, and it's always like, and then they go nowhere, and then they get into trouble, and that's every movie. Spoiler alert. Sorry about that. I have a cool demo of that also. So, what? Oh, shit. Thanks. Yeah, I'm gonna go a little bit over the question time to show this demo because it's cool. So, gonna make a new file called Hyperdrive. And it's very similar to the other one, so we're just going to copy paste most of it. Instead of calling it hypercore, we're going to call it Hyperdrive. And you instantiate that, and you get a drive out instead of a core, and you pass it in a level DB. And instead of making a feed, you make something called an archive, because it's kind of like a zip balls or a tuple. Zip archive, I guess it's called. That's probably why I named it that. So the method is called create archive. And then the thing you can do with this archive is you can write files to it. So you can do fs create read stream, and then gonna do this fun thing where we add our file itself to it. A little bit meta, but that's awesome. And then the only thing you need to do is create a file, write stream, and you give it a file name. Oh, cool. They said JavaScript was hard. You just need to have an audience yelling mistakes at you. Cool data.js. So you just need to have a file, and you can just pipe it into a write stream. And then let's print out the key again as we did before. So let's try and run this, see if this actually works. Oh, thanks. There we go, that's a little bit easier to remember. So then the other thing you can do is get the files out of it. So you can do cool things like archive, create, file, read stream, cool data.js, pipe, process, standard out. Let's try that. And then you get the data out again. That's pretty cool. You actually see that it's the old file I added because it's still writing files to it here. And as before, we can just use this cool hyperdiscovery module. And you can just call hyperdiscovery archive. And then if you run this on another computer, it should just work. Let's try that. Probably won't work because of things. So I'm going to go to my computer here again. Hyperdrive. And just paste the code in, deploy it, see what happens. I wonder if this will work. So I gotta run my local one. Still printing out the file, that's fine. And this is the remote one, and it replicates the file and spits it out. So no, it's a file share network that just works. And the cool thing is that this is also live. So you can do stuff like list what files are in the archive. And every time there's a new file, we'll just print out new file, then the name of it, and then we'll just print it out. We can do it shorthand here. We just say pass the data to it, and we'll print it out. And this should be live also. So if I run this, I'll print out the file. I guess oh, did I edit it here? Yeah, man. I edited it on my local computer. Stupid. It's hard when you have multiple computers. Oh, shit. Doesn't look good. Just delete this. That's my VI skills. Thomas is going to yell at me after this. There you go. Gonna try and run this now. So, running that, it says, oh, there's a new file that's called cool data. But the cool thing is this is live. So if I just pipe a new file into it locally, I'm just going to pipe the same file into it again because we changed it. It automatically replicates to the server, and the server spits out the new version, which is like the one where I commented this out. But it's also versioned because it's an append-only lock, so we actually have the old version of the file in there as well. You can just choose not to replicate it, but just replicated everything. So if I run this again, it actually first prints out the old version and then the new version. there's like a race condition here because I'm doing it all sync, but it doesn't matter. So it's actually both versions of the file. You get all the data. So you can choose which one you like, the best one. So if you like, old cool data, that's cool. I personally like new cool data better. So let's go back to this. So almost done. So basically, the only thing that is it's a command line tool and a desktop app that manages hyperdrives. So instead of oops, sorry about that. So instead of writing JavaScript applications for managing or replicating files, which is a little bit tricky for people who don't know JavaScript, which is like a lot of people, we can just use an app. So I have a quick demo of that. Oh man, cool. So what you can do is you can just go to your command line, go into a folder that has some files, the files I just wrote. Then you can do npm install -g dat. That's it. I'm not going to do it now because I don't have 10 minutes to wait for npm to finish. Just make sure there's no that here anymore. And then you can just do that and then give it the folder. If you do that, it just adds the files and prints out this cool hash, which is like the Hyperdrive public key. And then the only thing you need to do is send this key to your friend or a fellow scientist. And they can go on their computer and they can just do that, paste in this link, and then a folder name. And then the two instances will find each other and replicate, and they only replicate the diff, which is pretty cool. And then you can just choose to cancel this, and then you can go into the folder, and then you have the data. So it's pretty simple. We also have a desktop app that kind of does the same thing, where you can just do it all in a UI instead, which I don't like. I like using command line tools because I'm cool. Hope you're cool also. So this is that I used earlier that's only half replicated. And it's all real time. So that basically means that you can add this cool flag to it that says watch files. And then on the server, if you run this again, if I then go to my local machine and into the folder and add a new file to the same folder, kind of like I would do in Dropbox, then hopefully if I go to the server, the output is a bit messed up because I was resizing, but it automatically appeared here. It's called hello dad. So let's check that it's actually correct. And it gives you all these cool security guarantees and all that stuff. So how much time do I have left? 7 minutes. Oh, cool. I'll just go to the end of this. And there's also already a bunch of app builds on this already. There's this cool thing called the Beaker browser, which is basically just a browser, but it works with that also. So that's pretty cool. So let me just quickly show you that. So if I just start it up, this is how I start up apps. There's like an Electron app you can download also, but I like to do this instead. So it's just this normal web browser. And you can do normal browser things, like go to Google. It'll go to cool Russian Google. Has like this, it says Russia there, I guess. But you can also do other cool things, like take a dat and paste in a dat link. And then it'll replicate the dat. And actually, if you had an index.html file in here, it would have rendered that as an HTML page. I can do stuff like click on it and read it. And it's all offline and peer-to-peer. So if I turn off that I have locally here, it's turned off now. I can still go to Beaker and I can actually refresh this, and the data is still there because it's a peer-to-peer data structure. So once you get the data, it's always there. You can even turn off your internet and it's still there. So I like that. It's pretty cool. Finally, this other. Whoa, why did that happen? Man, I'm in some cool state now. Just do it like that. And finally, there's this other cool thing called Science Fair, which is the same thing, but just for papers. So it's just a cool Electron application that uses that to replicate scientific papers. So instead of having to download them all, you can just install this. It comes seeded with a bunch of papers from some sources they collaborate with, something called eLife, if you're familiar with data. And then it just replicates basically the metadata of this huge data set of papers, and then you can go in there and you can search for I want to learn stuff about cancer, and it'll search for the papers, and it'll find a relevant one and only download that one, all using that. So that's super cool. We wrote a cool paper about all this stuff. You can't really see the link, but it says PDF here. So, and that's basically it. That's all the stuff I showed. Will be online. Thank you.
Some time for questions, so I'll get a few. I'll be back.
Thank you.
Thanks.
One short question. In the code, you used just creating the storage, and then just write Hyperdrive
core.
No, to share.
Discovery.
How Hyperdiscovery. So how basically they share the link? It's any major point of exchanging?
Yeah, so it's a really good question. It's like the magic part of it. I should have called it Hypermagic instead. That would have been a better name. I wonder if that's available. I'll just check real quick. So it's a really good question. How I'm doing this, Hypermagic. It uses the BitTorrent DHT to find other people. So it takes that key and it generates. Oh, it's available. Cool. I'll use that. Don't use it. It's mine. It takes that key and it generates a token based on that key. Puts that in the BitTorrent DHT with your IP and port that you're listening on. Then other people will do the same if they have the same key issue, and then they'll find each other. Then they'll use something called stun, which is like a fancy word of doing fancy way of saying hole punching, to connect to each other. And you can connect to anybody even though you don't trust them because of the Merkle Tree. So you can actually connect to other people that you don't trust, and you know that they can only send you the right data because the key verifies it. And a really cool feature is that it actually uses the same key to generate an encryption key based on like a secret key system. So the traffic is all encrypted. So other people you won't be able to get the data unless you have the original key. Does that answer your question?
Okay, so this long hex is just a stamp of public key to verify the hash.
It's a 32-byte public key that corresponds to a secret key, and then it does all the things I talk about to do it.
Okay, thank you.
Thank you. And could we use Hyperdrive or whatever tech you showed on client?
Wait, say that again, sorry.
Could we use it not inside the node, but inside the browser?
Yeah, so it all works in the browser. As long as you give it a LevelDB, and LevelDB actually works in the browser using something called IndexedDB. The only thing that won't work in the browser is the BitTorrent DHT, which is why that's the discovery part is decoupled. So I'll just show you quick here. The only thing you need to do, if you're familiar with Node, is that it has this cool API called replicate. See if I can find it here, which is a stream. And as long as you pipe this stream to somebody else, they'll replicate. So in the browser, you could use that using WebRTC. We actually have a website. Oops, now I'm editing my slides all of a sudden. So we have a website called dat.land. which is just built of this. This is just a static website. And what you can do here is you can create a dat. Oh, it's still loading. Still loading because it's like has to download 5 megabytes of JavaScript on gzip. And then you can add a file, and then it just puts the link up here in the URL. So you can send that file, send that link to somebody else, and then that person, that browser will connect to the other browser using WebRTC. And to find each other, they use a distributed network to rerun that basically acts as a DHT. So you can click here, and you can see a cool picture of me when I had my beard. Cool. Other questions? Hey.
Hi. Great presentation.
Thanks.
How does that compare to IPFS?
So it's a good question. Give me 40 minutes to explain all the differences between all the distributed systems. So that is basically just at the core of it an append-only lock. And the very most important feature we do is real time. So it's not a static file sharing network where you have a hash. It's all about real timing, pushing up updates fast. So that's the main difference. That's the thing we focus on. That's the thing, in my opinion, that IPFS does the least well. It does a lot of things really good, but that's the thing it does the least well. So real time is basically the key of us. If you look at just static file sharing, IPFS, BitTorrent, that is kind of in the same group. Everybody of applications, each with like probably 10-20% difference in some edge cases where we pick a different trade-off than BitTorrent. IPFS picks a different trade-off than we do. But the main thing we focus on, where we put all our energies in real time and in the diffing. If that answers your question, it's like hard to answer that in 2 minutes, but yeah. Hey, what's up?
Speaking about distributed systems, this third diffing. Actually, yeah. What context? I just wonder how performant your solution in context of speed and also conflict resolution if there is some concurrency.
Right. So it's a good question. So in terms of speed is hard to argue against because when we talk about speed, we need to compare it against something else, right? So the easiest thing to compare file sharing against, the big classic benchmark of file sharing, is either HTTP, which is like download from one server, get the data, and if you have a good server, that's probably always going to be faster because it's going to do less things. Yeah. No, I'm getting to that. 1 second. So it's pretty fast. In the benchmark we've done, it will always saturate your network before saturating your CPU, which is the thing we care about. Hashing is super fast on modern computers, so it's not really an issue. You can run it in the browser with very little concern. In terms of conflict resolution, it's up to, if you use the module, it's up to you to figure out which version you want. You can just list all the available versions and then you can pick the one you want. So for actual science use cases, the idea is that scientists, when they publish a paper with some data in, they'll put a link in there that's like the live link, but also with a snapshot of the data they actually meant. So it's equivalent to sharing a Git hash instead of just a reference.
Давайте мы пообщаемся после, извините. Yeah, that's.
So in terms of merging, right now it's I think right now it's just last one wins, but the API allows in the CLI, but the API allows you to do cool stuff, and it's so you can implement. It's like the stupid answer, but I'm going to say it anyway. You can do it however you want, because I can't make that decision for you. It's up to the implementer to make that decision. So if you wanted to make a merge model, you could do that. If you wanted to have last one wins, you can do that.